friends, I welcome you all for another lecture on the course Microprocessors and Microcontrollers. In this lecture, I am going to discuss about a concept, a real mode operation of 80386. We know that our 80386 operated in three different modes. One is a real mode, second one is a protected mode, and third one is a virtual 86 mode. Generally, virtual 86 mode only exists in protected mode itself. That I discuss in later. But in this class, I am going to discuss about the real mode operation of 80386. Right. Generally, it is a default mode operation of 80386. That means, once you switch on your 80386, straight away your 80386 operates in this real mode. That is the meaning of default mode operation of 80386. A real mode is considered as default mode of 80386. And coming to after reset of 80386, it starts program execution from the memory location address, that is 0 followed by 7FH. That means once you reset your 80386 processor, it stops the current executing program and it shifts execution to initialization program of your 80386. The initialization program of 80386 was occupied in last 16 locations of its addressable memory. The last 16 bytes start from an address 0 followed by 7FH. From that location to 8FH. 8FH that indicates the last 16 bytes. Last 16 bytes, which is F, 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 H. So from this to this, there are total 16 locations. That means your initialization program of 80386 was available in last 16 locations of your 80386 addressable memory. This is the meaning of this. This was executed only in a real mode operation. So that's the meaning of this. Coming to next, in this mode, your 80386 works as fast 8086 with a 32-bit. It is not one, friends, sorry. It is a bit. 32-bit registers and data types. That means in a real mode operation of 80386, it just looks like fast 8086. We know that, friends, 8086 is a 16-bit processor. In real mode, your 80386 looks like a fast 8086 because it will use a 32-bit registers and it will use a different data types. So that it is looks like a fast 8086. That's the meaning of this. The real address mode is in effect after a signal on the reset signal. Even if the system is going to be used in a protected mode, the startup program will execute in real mode itself. What's the meaning of this statement, friends? The meaning of this statement is whenever our 80386 identifies logic 1 over a reset signal, then automatically your processor resets. So in that case, it is entering into a real mode itself. Because in a real mode itself only, it will go and execute the initialization program of 80386. This is the first half of this. And the second half is, if we want to operate our 80386 in a protected mode, we can't directly move to protected mode itself. First we are operated in real mode, then only we are shifted to protected mode. That means your 80386 enters into protected mode only from real mode only. It can't directly goes to the protected mode. So that is the meaning of second half of this particular statement. What's the first half of the statement? Once your 80386 identify a signal or a reset, that means once your 80386 identify valid signal on a reset signal, automatically it stops the current executing program, it will go and execute initialization program, it executed only in the real mode. And second half is, if you want to operate our 80386 is in a protected mode, no doubt, first of all your 80386 must be in real mode. From that on only we can shift to protected mode. There is no direct way directly entering into protected mode operation of 80386. This is the meaning of last statement. And next, in real mode, the 80386 can address at the most of memory size is only 1 MB physically. That means already we know that 80386 acts like fast 86 in real mode. We know that 8086 can address up to only an MB of 1 MB of physical memory. That's why here also in the real mode, your 80386 can address at a maximum of a memory was 1 MB by using an address line that is A19 to A0. But your 80386 has total 32 address lines, that is from A31 to A0. But out of I'm using only 20 address lines, A19 to A0, because in real mode our 80386 lacks like fast 86. In 86, just it has only 20 address lines. With the help of them, it can address up to maximum of a memory 1 MB. So that's the meaning of this. And one more important thing is paging unit is disabled in real mode. Because in 8086 there is no existence of a paging unit. So that in real mode operation of 80386, the paging unit was disabled. Once the paging unit was disabled, what are the real addresses or logical addresses that are generated by the processor, those are considered as physical addresses. That's the meaning of this. A paging unit is disabled in real mode, and hence real addresses are the same as the physical addresses. Once your paging unit was disabled, there is no conversion of a real address into linear addresses. So that's why here what happens is your paging unit directly whatever the real addresses has, it is converted to physical address. Sorry guys, a physical paging unit what it do is, it will convert a linear address into physical address once your paging unit is exist. So that's why here a paging unit is not exist. So the linear addresses or real addresses what are generated by your processor, those addresses straight away is considered as a physical address because the paging unit was disabled. That's the meaning of this. Next, to form a physical memory address, appropriate segment register contents 16 bits are shifted left by 4-bit positions and then added to a 16-bit offset address. So, what is the point here I was mentioned? It is already coded in 8086 because in 8086 the physical address how it was produced is first it will access a base address from appropriate segment register via summer circuit. Then a summer circuit shift that base address which it was accessed from a segment register to left side by 4-bit positions. Thereafter only it will go and add an offset address of a size 16-bit to it in order to get a 20-bit of physical address. The same procedure 80386 follows in case of real mode of operation. So that's the meaning of this. So what are the segment registers? It has to go and access the information. That segment register contents first shifted to left side by 4-bit positions, then a 16-bit offset address is added to it in order to get a 20-bit of physical address. So that's the meaning of this particular statement. And next important thing is, in case of a real mode of operation, the segment size is just only 64 kilobytes because 8086 segment size is equal to 64 kilobytes. In real mode operation of 80386, it just acts like a fast 8086. So that your segment size is just only 64 kilobytes. Next, the segment in 80386 real mode can be read or write or executed. That is, no protection is available. So no protection mechanism is available in real mode operation because in real mode it just acts like fast 86. In 86 case there is no protection levels. So that in real mode of operation there is no protection to access, to read or write or execute an information to or from a segment. That's the meaning of this. Any fetch or access past the end of the segment limit generate exception 30 in the real mode. What exception is? Exception means a runtime error. Whenever if you want to try to access the information from a segment, once the address of a segment crosses its limits, we are unable to access an information from that same segment. We are access information from some other segment. Once such situation was exist, then immediately your processor may generate an exception 13 that indicates an error condition. We are not accessing an information from what are the segment you want. So that's the meaning of this. And another important thing is the segments which are present in this real mode operation, those segments may be either overlap or it may be non-overlap. Once the segments are overlap, that means there is a common area for two segments. Once you have a common area for two segments, the area which are overlap, those locations we can access in two different ways. By considering of this segment we can access, and by considering of another segment we can access, so that we have more flexibility. But sometimes your segments are non-overlap, that means there is no common area between the two segments. So in real mode operation, your segments may be either overlap or it may be non-overlap. And last important point, the IVT means interrupt vector table IVT. IVT means interrupt vector table. The IVT of 80386 has been allocated 1 kilobyte space starting from 50H2 003 FFH. This is also from 8086 only. In 8086, interrupt vector table is only available the first 1 kilobyte of memory space of its addressable memory 1 MB. That means that the locations from 50H2 003 FFH and found interrupt vector table. What is interrupt vector table? It is a table which provides interrupt service routine address of 256 types of interrupts which are supported by our 8086. So that the same point repeated here, the IVT of 80386 has been allocated 1 kilobyte of space starting from 50H2 003 FFH. So this is another important one. Next, how this physical address can be calculated in case of this real mode. So see here guys, an offset address size is equal to 16 bit, and this is your segment selector. I am already told you that appropriate segment provides a segment selector information that is shifted to left side by 4 bits. Once you shift it to left side by 4 bits, what happens is on the right hand side there are 4 zeros are exist. Then 16-bit number becomes a 20-bit number. That 20-bit number is given to one of the input for a summer or an adder, and another input is nothing but your 16-bit offset. By adding of these two, I may get a physical address of size of 16-bit, that is this. I am already told you that the segment size is a total 64 kilobytes, that is from this to this. So total memory your 80386 can support in case of real mode is equal to only 1 MB. In that the segment size is equal to 64 kilobytes. This is a way how your 80386 can produce a 20-bit physical address in case of real mode. Simply what it do? It will simply took the segment selector information from appropriate segment register. Later it is shift to left side by 4 bits. Then you may get a right hand side 4 zeros. Then it is a 20-bit address. This 20-bit address is given to one input of your adder or a summer. 16-bit information I was getting from an offset. By adding of these two, I may get again a 20-bit physical address. And one more important thing is what your 20-bit address is considered as the starting point of your selected segment itself. So this is the way how your 80386 can calculate a 20-bit physical address in real mode operation. So I hope you understand the real mode operation of 80386. In the next class, I'll go and discuss about the protected mode operation of 80386 along with virtual mode. Thank you for patient listening.